Yet there is another factor, one far more dangerous and still vastly underestimated, in how nanoplastics affect the human body. It is precisely this factor that allows nanoplastics to easily penetrate the body's protective barriers, and once inside, they are virtually impossible to remove. At the micro and nanoscale, plastic particles acquire new physicochemical properties. They can retain surface charge for longer periods and interact with electrostatic fields and other molecules. In this sense, micro and nanoplastics can be compared to an electret, a material that accumulates static electricity and holds it for an extended time. Moreover, plastic particles not only retain an electrostatic charge, but can also recharge it. This occurs through the triboelectric effect. That is, when plastic comes into contact with or rubs against other surfaces, including fabrics, cells, and liquids. In other words, plastic particles can recharge themselves, restoring their electrostatic charge again and again.
To understand how the properties of plastic differ from those of other materials, we conducted a simple experiment. Here, inside transparent plastic cups, we suspended several objects made of different materials: a metal needle, a wooden matchstick, a copper wire, and a strip of magnesium. Now, while these objects remained motionless when a plastic rod was brought close, everything changed dramatically when we rubbed the plastic rod against the wall. That is, all the suspended objects began swinging and moved toward the rod. So, what caused this reaction? The answer lies in the electrostatic charge that formed on the plastic surface. For example, a wooden rod, unlike plastic, cannot hold such a charge. Even after rubbing it with wool, the material caused no movement. The same was true for metal scissors, which showed no effect until the material touched a magnet. Only then did the metal needle respond. So this experiment clearly shows how material responds differently to electric and magnetic fields. Now, plastic stands out among other materials because it can not only accumulate, but also retain electrostatic charge for a prolonged period. This is distinct from wood, which quickly dissipates charge because of its moisture content, and therefore has little effect on other nearby objects. It's a dielectric material. Metals, on the other hand, do not hold charge but quickly redistributes it across their surface. They're conductors. Magnets, meanwhile, create magnetic rather than electric fields and thus cannot attract electrically neutral objects in the way a charged plastic can. So this is what makes electrostatically charged plastic so dangerous. It is an invisible force capable of changing everything around it. Once charged, plastic can attract even neutral particles, disrupting many natural physical processes. And as plastics breaks down into smaller fragments, micro and nanoplastics, it doesn't lose its properties. In fact, the impact of plastic on the environment and living organisms only intensifies as the particles become smaller. It's the charge that makes plastic especially dangerous to all life on our planet.
Therefore, plastic cannot be regarded as passive waste. It is an active, electrically charged material capable of interacting with nearly all substances on Earth, from atmospheric particles to living cells. The smaller the plastic particle, the more active it becomes, and the more dangerous its impact.
If you view a microplastic particle and it's 5 millimeters in diameter, and you break it down to a nanoplastic particle, which is 1 micrometer in size, you generate from one particle 125 billion particles, which is the number of galaxies we have in the universe. And the surface of these particles is 5,000 times larger than the 5 millimeter particle. So this just exemplifies how big an issue the breakdown of those plastic particles in even and all the time smaller particles. And these particles have maybe totally different properties than the large 5 millimeter particles. So you not only change the size, but also the surface and the properties of the particles.
Nanoplastic has an enormous surface area compared to its mass. It's like a tiny grain with the surface area of a football field. This is called a high specific surface area. The larger the surface, the greater the particle's ability to accumulate and retain electrostatic charge, and the more active sites it contains that bind proteins, metal ions, lipids, and other molecules from the surrounding environment can attach. To understand how dangerous these tiny charged particles are, let's run a simple mental experiment. For example, we have an ordinary 1.5-volt battery. If we divide it into 125 billion tiny batteries, and suppose each of them still had the same power output of 1.5 volts, their aggregate power would equal 187.5 billion volts. Imagine how much greater the voltage will become. Similar things happen with plastic. When a single fragment of plastic is divided into 125 billion particles, each carrying a charge, the amount of charge increases.
Today, millions of tons of plastic in our biosphere are constantly breaking down into smaller and smaller particles, each carrying an electrostatic charge that allows it to penetrate everywhere. Consequently, as the number of electrostatically charged plastic particles grows, and excess electrical potential builds up throughout our planet. This is a major factor disrupting the Earth's energy balance, contributing to warming of the oceans, increase in atmospheric anomalies, as well as the number and severity of natural disasters each year. Note that the warmer the ocean, the more acidic it gets, and the faster plastic breaks down into charged micro-nanoplastics. This in turn leads to greater buildup of energy on our planet, amplifying all these processes in a self-reinforcing chain reaction. In addition, the smaller the particle, the more easily it penetrates the protective barrier of living organisms, including humans, triggering various chronic diseases and killing millions of people. We'll explore all of this in detail.
In other words, plastic fragmentation does not make it safer. On the contrary, it transforms it into nanoparticles that readily penetrate living organisms.
We know so far that compared to microplastics, nanoplastics can pass through the cell membranes much easily. That means that they can go to our bloodstream, not just us animals as well, and they can be carried to certain organs, deposited there, hard to be excreted back and things like that.
This is why nanoplastic is far more dangerous than microplastic, as its capacity to accumulate electrostatic charge is significantly greater.
Due to their electret-like behavior and small size, plastics do not remain inert particles. They become charged and transform into trillions of micro and nano killers. It is through this charge that tiny plastics can penetrate deep into living tissues and even destroy them. Today, these particles are everywhere, and they're already interfering with the delicate electrical processes in nature. Now, we often think of electricity as something artificial, confined to light bulbs, batteries, and wires. But in reality, electrical impulses are the very language of life. That is, they enable the entire biosphere to function. And it is precisely these natural processes that electrostatically charged micro and nanoplastics are now disrupting.